this is too nice to believe, right? It's got so much going for it. It's got a 0 in the limit. It's got a polynomial in there. You're great. So you get 16 minus 8. With zeros next to it, you get 8 pi. Sweet. So that'd be some weird little pedestal thing, or it looks like a top, actually, if you think about it. If you rotate that sucker around, you get this little point at the bottom, right? If we attach the little thing on the top, you choo, right? Leo can see what level he's in. Don't watch that movie, Inception. So if we try this, let's try this again. Let's try it with shells. Let me redraw this. Going around the x-axis. So if I have to do shells, or if I choose to try shells, it's got to be integral d what? Start with dy. I love it. So that's the first thing you memorize and get down. Washers, discs, the d piece is exactly the thing that I'm rotating around. Parallel to the x-axis dx, parallel to the y-axis dy. Shells, other way. That is one big reason why whatever one can't handle, the other one can. And vice versa. Now, with shells, what I want to do... Now, how are my rectangles going to be oriented here? And what do we just figure out? dy. So I got to march along the y-axis to find my rectangles. So they're going to be like this. They're always perpendicular to the axis you're rotating around. But if you think about it, the minute you write dy, that means that the y-axis must be where you're marching. Oh, there's a rectangle. And you march a little bit. Oh, there's another rectangle. That's the idea. That's how I find my rectangles. I find a rectangle. I rotate it. And I add that in, because now I'm going to move to the next one. I'm going to add the next one I marched to, rotate it, add that in. Add it, and I just keep on going. That's what this does. So drawing this rectangle is stupid useful, because how tall is a rectangle going to be? What's the height of a rectangle? How tall is it? It starts at... What's the value of y here? 0. And it goes to, what's the value of, what was this again? This was, we need x in terms, we need y in terms of, I need x in terms of y. Oops, y squared. Is it with square root of x? Yeah, okay. So how tall is that rectangle? It starts at x equals 0 and goes out to x equals y squared. So the height of a rectangle is y squared. So that's kind of like why I like this interpretation, because once you have to break this down, it's like, well, it could be this, or it could be this, or it could be a difference of 2, and that's not very useful. It's just if you draw a rectangle in, see what's involved, and figure out how tall it is. Here, this started at x equals 0, and went to x equals y squared, so it's y squared. That's how tall it is. That's going to go in, so let's see what we got. We got 2 pi. The height is y squared. And now what's the radius? Here's the axis of rotation. How far out do I have to go to find a rectangle? That's what it's doing. But where is a specific rectangle located? At a y value. So the radius is y. So if my rectangles are on the x-axis, the radius is going to be x. It could be x plus something or x minus something if my axis is off. But it's going to be x plus minus. Here it's dy, so it's going to be y. If I was rotating around y equals -1, then my radius would be y plus 1. The radius is how far you've got to go to get to a specific rectangle. Now, yes, the values for that go from 0 to 2, but this right there, what is that? That's y. I don't know, it's some y value. It's on the y-axis. It's some y value. Okay, there you go. That's the radius. That's how far I've got to go to get to a rectangle. If I had a specific rectangle I wanted you to go to, what would I have to tell you? I have to tell you the value of y to stop at. That's why the radius is y. I have to give you, that's the value I got to tell you, so you can stop there and go, I'm there, see it. And now, I mean, look at this. And again, what do I put my limits based on? So it's going to be from 0 to 2. That, so many times I look back at this to keep myself straight. Okay, I like it. And now that's a relatively easy integral. It took a while to get there, which makes sense. It's just like a word problem, really. It takes a while to set it up, and then when you're there, it should be quick. So you get 2 pi 0 to 2 y cubed. 2 pi, what's the integral of y cubed?
1/4 y, so forth.
I like it. From 0 to 2. So I get 2 is to the 4th is 16, divided by 4 is 4, times 2 is 8 pi. Holy shit. All right, let's do another one. Every time we do one, I think you guys make some more connections. We do one more with you, and then I'm gonna let you try some on your own. Which I love when people will gripe about that. I'm like, holy shit, you want more things on your own that I'm not grading. You want that. Let me leave this here. I might reference that. Let's do one that's a little different than any we've done so far. You're not going to like to hear what I'm about to say, but we've been doing relatively easy ones in terms of where the axis of rotation could be. Let's see if I can find one that's doing what I want it to do. Yeah, okay, perfect. I can't remember. All right. So bounded by y equals x and y equals x squared, around y equals 2. Doesn't matter if that's what it says. That sounds good to me. First thing, try to do a rough sketch. It's bounded by these two, but dear God, where they meet should be easy to find. Myself a little more. All right, so what's this little region look like? They meet at what points? If you have to, x squared equals x. That's what you're curious about. Subtract the x. Take out the x. So we meet at 0 and 1. Which you should be able to see by just looking at it. So 0, 0, 1, 1. Y equals x goes there directly. Y equals x squared actually goes there underneath. When you square a number less than 1, it actually gets smaller. So that's another little sort of banana. Very strange, flat-sided banana. So it'll sit on a table. So I'm going to rotate that around this line. There's a lot going on there. I don't think we've done one yet where the axis of rotation is like above the region we're rotating. But nothing really changes. Let's see if you guys can get the math and how it doesn't change. What method do you guys want to use first? It's wide open. All right, so let's try washers. Let's see if we run into a snag or you think there is really something about the method you chose that's wrong, just back up, try the other method. There's a very good possibility of that happening. If it never happens to you, then that probably means you're not doing enough. So let's see, what's the inner radius going to be? And I've said this a couple times earlier. How do you figure out how long something is? Bigger minus smaller, right?
2 minus x.
Beautiful. So, yeah, and we're rotating around. Really, the very first step, Jeff, is if you guys picked washers, this is going to, of course, be integral d x. So I do want everything in terms of x inside. I like it. So this is going to be, so the inner radius is going to be 2 minus x. 2 minus x. How do you check that? Well, how long should it be right here at the extreme? How long should that be? That should be 1. And that's at the point where x is 1. You plug a 1 in, you get 1. So at least do that. That's a real quick place to see if you turn something the wrong way. If you get negative 1, you're like, holy shit. Radius can't be negative. I made a mistake. We stop here. I think a lot of people, there's a lot of ways you can overblow a lot of this because certain parts of this procedure are very simple. But a lot of us just say every part of this is hard and then you just overdo things. This really is just how long is that arrow I just drew. It really is. If it changes based on where you pick to draw it in the region you're talking about, then it's going to have some dependence on x. That's how it can change. If it's constant, that kicks ass. There must be a constant wall. It doesn't change anywhere. It's going to be just a number. It kicks ass. What about the outer radius? Let me get rid of these. Beep.
2 minus x squared.
Where do you go? 2 minus?
X minus x squared.
No, again, see, you're trying to take into account the other wall. The other wall doesn't matter worth anything. It's just, careful, not just 2, because it changes, doesn't it? Here it's smaller. So it's 2 minus, and you started it off right, but then you went too far. It's just 2 minus x squared. All right. And so now that's real. Once I got those two, I'm basically ready. What are my limits going to be? 0 to 1. You can't go wrong with this one. Pi, and then I got my r outer squared minus my r inner squared. So when you rotate this around, can you see how that would make another one of those bowl things with a hole in the middle? I don't know if you guys can really see that. If I rotate this, let me try to do it. You don't have to do what I'm about to do, and you don't even want me to do what I'm about to try to do, because it's going to suck so bad. But I'm going to do it anyway, because I'm crazy. So if you draw a mirror image of this, where am I at? There I am. So it should go out like this. And I rotate like that. I rotate around. So you see how this whole middle part is going to be empty. This is the hole there. right? Maybe? That's horrible, I know. That's too damn bad for us. So this edge is just going to get rotated around. It's going to be solid here, but it's going to be this huge hole at the top, and it goes down to the smaller hole at the bottom. It ain't going to hold anything. It sucks. Hopefully you're supposed to put it over something. Okay, it's a horrible, horrible bowl. All right, and now the rest of this I don't even want to do. You guys should be able to do this in your sleep a little bit. Minus 4 plus 4x plus, minus x squared. And then you integrate and you plug numbers in, what to do. Right, those limits are nice. Yes, sir?
So the reason for both disk and washer that's being times by pi is because it's a circle, and then for shelf it's 2 pi because you're taking 2 circles, kind of?
It really is. Let me see. If I rotated this and then looked at a cross section, it would look just like this, right? And the inner radius, the outer radius. So it is the area of the big circle minus the area of the small circle. I mean, that's why I call it cookie cutter. So I just factor a pi out of both so I can have on the inside the x dependent stuff. Yeah, pi is all constant, just come out. The other one is because it's about the surface area. It's the surface area of this. So what's the circumference of this? That's 2 pi r. That's really the only reason why it's 2 pi. Right? Yeah, okay, I like it. So you start with this circumference and then you multiply it by the height. That gives you the surface area. Here I'm taking the area of a disk and the area of this, so that's why it's no 2 there. Yeah, all right, I like it. If I try to do that one with shells, let's see where we get to with shells on that one. Let me take this away up here. So shells would require, let's see what do I really need here. It's really tiny, Jeff, but oh well. So if I'm going around y equals 2, and I'm doing shells, first off, so if I'm doing shells, how would the interval be set up? Interval d, yeah, because I'm doing something parallel to the x-axis, so it's got to be dy. I like it. So immediately I could do the limits before I do anything else. What is y doing? 0 to 1. Okay, because the minute you start doing other things, you start thinking too many, like this is going there, and this, no. That's all y is doing for the region I'm talking about. I like it. Okay, now, for shells, since I'm doing around this, my rectangles are they going to be laying down or standing up? Laying down, 11. They always have to be, how do I want to say this? So, all right, because then I'm going to rotate that around, and that's how I make that shell around. I like it. Okay. So how tall is that going to be? So now since it's dy, this is the line, this is x equals y. This one is x equal to square root of y. Right? It's y equals x squared. So what happened? What'd you guys say? You're like, I'm not going to tell you. All right, I'll live with it. Is everybody cool with what's happening? No? Okay. So how tall is that rectangle? What's the height of that rectangle? No, come on.
Root y minus y.
Yeah, it's going to be the top one, root y, minus the bottom one. See, so shells there's a lot of the shells method that's a lot simpler, to be honest. The height is always just, it doesn't give a shit where you're rotating around, whatever. When you draw a rectangle in, it don't care where it's going to get rotated around. It just sits there. So you can see what the height is. It has no consideration about what the rotation axis is or anything else. Now, if I want to get the radius, which is what I want to get, how do I locate that guy? In relation to the axis, or always in relation to the axis of rotation. So how far away from the axis is this one? Well, that's at some y value. And this, of course, was 2. Say it?
1 plus y.
No.
2 minus 1.
2 minus y. What is it always? It's always big minus small. I want you to really... So that's why it doesn't matter where I put the axis of rotation. If it's the biggest thing, I do 2 minus function stuff. If it's below everything, I do function stuff minus it. Right? The other ones we were doing were mostly like negative stuff, and we kept adding, because it was this minus negative. That's why I added that extra shit on. If I put it above the whole region, it's now the big dude. Come on now, stay with me. How do I find distance? Bigger minus smaller, right? The difference between two ages. I wouldn't do small age minus big age. Like, you're negative 11 years more. What the shit are you talking about? All right, where am I? So the radius is going to be 2 minus y. That's how far away from the axis I have to go to find any rectangle. If you're concerned about, well, how does that eliminate this? Is anybody worried about that? You're like, well, that has no restrictions. Well, the restrictions are going to be right there. It's got to live between 0 and 1. It's already set. You don't have to overthink that step. You're like, dude, this should be called overthink chapter. That's all I'm going to do. I understand. Okay, so now I can put everything together. I got my 2 pi. I got my radius. And I got my height. And in this case, the washers were pretty straightforward. This was not that horrible, to be honest. If you rewrite this as y to the 1/2. So let's see. I didn't really figure that out, did I? So I don't know. If you did both of these, it should come out to be the same. Let's see, 2y to the 1/2. Minus 2y minus y to the 3/2 plus y squared. If you integrate that, throw the limits in, multiply by 2 pi, it should come out the same answer as that. It's got to, just like we did before. It's just you don't need my help to how to plug 1 in. You can do that. Yes?
Is that y to the 3/2?
Yeah, let's see. Y times y to the 1/2? Oh, yeah, yeah. It's 3/2, yeah.
It's 3, right?
Yep. Whoa, holy shit. I really blew it up for you. Yes?
So, if the axis is not specified as a value, it is just x or just a variable. So, like seeing how like it says it's around x, y over y2. So,
Around y equals 2, yeah.
Yeah.
They can't leave that out.
It's okay, but if the question was just saying around just the y-axis, it would just be y.
Yeah, if it was around the y-axis, then that radius would be just y.
Okay.
And for this kind of problem where it's dy, totally. So that's why I said the radius is always just x or y, or you might have to adjust it depending on if you put the axis somewhere else. But it's always going to be something related to y or x, depending on what you do, if it's dx or dy. And the beautiful thing is, how do you tell if it's dx or dy? Just by what you're rotating parallel to. It's almost too nice to believe. Okay, so let's do this. I think I want you to do the colorful side first. It's a little specific thing about a certain problem that can only be done with shells. And then the other side is just general shell and washer practice. It's a mixture of the two. All right. So you guys can work together if you want to. So do try to set it up like as a discs problem, and see if you can tell why that's not the way you want to do it. And just in case you're curious, the drawing here is the actual drawing of that function. These were just some nice images I wanted to show you about the idea of it. This is the one you can mark on as far as finding your rectangles and so forth.